Okay, hello everyone. So last time we proved the result about Ramsey numbers. So we proved that if n choose k times 2 to the power 1 minus k choose 2 is less than 1, then we can say that the Ramsey number k and k is bigger than n. And then we use this result to find the lower bound for exponential lower bound for Ramsey numbers. Now today we will remove the condition of this theorem using expected values. Okay, so remember that in this course, the goal is to use probabilistic methods to prove results about graph theory and in particular Ramsey theory. Now, one common method or technique of probability theory is using first moments, or also called expected values. Another method is using second moments, which we will get to it later. But today we will use expected values or first moments to derive a result or prove a theorem that has no condition on n and k. Well, right now, if you want to use this theorem, well, n and k should satisfy this condition, then you will be allowed to use the theorem. Otherwise, you're not allowed to use the theorem. But in the theorem that we'll prove today, it has no such condition, and you're always allowed to use it for any values of n and k. Okay, so first let's remind about expected values. Again, I'm sure you know about it. Just a quick reminder. Recall for a random variable x, and the expected value. If we say for a discrete random variable x, the expected value is defined as follows. So expected value of x, if you remember, was sigma for the discrete random variable, sigma x p of x, and the sum is over all possible values of x, and this means sigma x probability that capital X is equal to small x. So the sum is over all possible outputs of capital X. Remember, capital X is a random variable, therefore it's a function from the sample space to real numbers. Okay, now, well, right now we can see a connection between expected values and probabilities, because you know all these P of X are the probabilities of capital X equals X. But let's say if you want to have a more direct connection between expected values and probabilities, that would be nicer, because again, the idea in this course is to try to prove existence of a particular construction by showing that the probability of existence of such construction is positive. Okay, so if we can have a more direct connection or relation between expected values and probabilities, it would be nice. And to derive such relation, I'm going to consider a particular example of or case of a random variable. So in particular, if capital X equals 1a, the indicator random variable, corresponding to an event A, then okay, so I'm here setting capital X to be the indicator random variable corresponding to an event. So we talked about this in the review of probability theory in the previous lectures, but if you need a reminder, quick reminder one more time, let me tell you that 1a, the indicator random variable, is defined like this. So 1a of omega is equal to 1 if omega belongs to A, and it's 0 if omega does not belong to A. So remember to define a random variable. Random variable means a function from the sample space to real numbers. And to define a function, you need to assign one output to each input, right? So the inputs are small omegas, elements of the sample space. Now the output is going to be 1 if omega belongs to A, and 0 if omega does not belong to A. And A here is an event. Event means a subset of the sample space. Now A is fixed. You want to define 1A of omega, so you have to just look. If omega is in A, output is 1. If it's not in A, the output is 0. Okay, so for such random variable, what can I say about the expected value? So expected value of X is equal to expected value of 1A. And this is sigma X, P of X, let me say probability of 1A equals X. Now, the sum is over all possible outputs of the random variable. Right now, the random variable is 1A, and it has only two outputs, either 0 or 1. So this sum will consist of only two terms. 1 times P of 1A equals 1, plus 0 times P of 1A equals 0. Now 0 times anything is 0. So we are left with P of 1A equals 1. Now 1A equals 1, or in general, capital X equals 1 is an event. What type of event is it? So this is by definition, probability of all elements omega, such that 1A of omega is 1. Again, in the review lecture of probability, we said that capital X equals A is an event consisting of all elements omega, such that capital X of omega is A, and A here is 1. So all elements small omega, such that 1A of omega is 1. Okay, what is this set now? This set is exactly A, capital A. Why is that true? Well, because by definition of 1A, every element in A has the feature that 1A of those elements are 1. Every element in A has the feature that 1A of that element is 1. And also, every element outside of A has the feature that 1A of that element is not 1. In other words, what I'm saying is that 1A of omega is equal to 1 if and only if small omega belongs to capital A. So this means this set here is exactly same as capital A. So probability of this set is probability of capital A. Okay, so we proved that expected value of 1A is equal to probability of A. Similarly, if let's say capital X is equal to 1A1 plus 1A2 all the way to 1AK for events A1 to AK, okay? And we know that the expected value is linear, right? So expected value of X plus Y is equal to expected value of x plus expected value of y. Therefore, expected value of the sum of these random variables is sum of the expected values, and each expected value, we just showed that, is probability of AI in this notation. So for events A1 to AK, then expected value of X is equal to P of A1 plus P of A2 all the way to P of AK. Okay, so this is one result that we need today, a connection between expected values and probabilities. Now another result that we need today is, again from probabilities, is the fact that if X is a random variable with mu equals E of X, then probability of X being bigger than equal to mu is positive, and also probability of X being less than equal to mu is also positive. Okay, let's see why this one is true. Proof of remark. So to prove P of X being bigger than equal to mu positive, assume on the contrary that P of X bigger than equal to mu is equal to 0. So I'm using proof by contradiction here. We want to prove that P of X bigger than equal to mu is positive. So let's assume this is not the case. And this would mean that P of X bigger than equal to mu has to be equal to 0. Okay, now let's see what type of contradiction we get here. Then expected value of X, which by definition is equal to mu, is equal to sigma X P of X over the sum is over all possible values of X. Now I want to break down this sum as sigma X P of X with X being less than mu plus sigma X P of X with X bigger than equal to mu. Okay, so see, small x here is a possible output of capital X, and it's a real number. Outputs of a random variable are real numbers. Now, every real number is either less than mu or bigger than equal to mu. There is no third possibility. So I can break down this sum into these two sums. Now, what is my assumption here? My assumption is that P of X bigger than equal to mu is equal to 0. So that means probability of every X, that probability of capital X equals a number, any number bigger than equal to mu is 0. When we say probability of capital X greater than equal to mu is 0, that means probability of X equals to any number bigger than equal to mu is 0. Therefore, this means that every term that you see here okay, so every term that you see here in this sum is 0, because P of X because here, remember the notation small p of X means probability of capital X equals small x. So small p of X, which means probability of capital X equals small x, is 0 for every small x bigger than or equal to mu. So every term here in this sum is 0. Okay, so I'm going to be left with only the first sum, x less than mu. Now I can say that this is less than sigma mu times P of X. Sum is over X, right? Because, well, every small x is less than mu, so I can say that this sum is less than this sum. And this one is I can take mu out. So mu times sigma p of x less than mu. Now I can say that this one is less than or equal to mu times sigma p of x, the sum over all x. Sigma p of x, the sum over all x is bigger than or equal to sigma p of x, where x is less than mu because every probability is non-negative. And then this is, what is the sum of all p of x? For the sum over all x is 1, right? So this is equal to mu times 1, which is mu. Okay, so let's see what we proved here. Say I started with e of x equals mu. I did some manipulation and I got this is less than this, which was also mu. So basically I've proved that mu here is less than, is less than, again, mu here. Okay, so we proved mu is less than mu. And this is obviously a contradiction. This contradiction implies p of x bigger than or equal to mu has to be positive. Similarly, one can show that p of x less than or equal to mu is also positive. Okay, so now we are ready to prove the theorem that I promised earlier. So theorem, let n and k bigger than or equal to 1 be integers, then capital R of k and k is bigger than n minus n choose k 2 to power 1 minus k choose 2. Okay, so this expression is probably familiar for you. This is the expression that previously in the previous theorem was appeared in the condition of the theorem. Now it's appeared in the statement. Now the advantage is that it's no longer in the condition, so we're allowed to use this theorem for any values of n and k. Now also let's see what is the connection between this theorem and the theorem we proved last time. So remark the connection between this theorem and last lecture's theorem. So last lecture theorem, if you remember, was saying that it has a condition. It had a condition. The condition was that if n choose k times 2 to the power 1 minus k choose 2 is less than 1, then so today's, let's say, today's theorem, by today's theorem, I mean theorem above, implies, what does it imply? Now see, if this number here is less than 1, so then I can say that capital R of k and k is bigger than n minus something less than 1. N minus b, capital R of k and k is an integer, n is also an integer. Now if I say that an integer is bigger than n minus something less than 1, means that integer has to be bigger than or equal to n itself, right? So implies capital R of k and k bigger than or equal to n. Last time's theorem implies, if you look at the last time's theorem, it was implying R of k and k bigger than n. So they're almost same. So last time's theorem was slightly stronger in this sense. So under this condition, today's theorem is slightly weaker, just slightly weaker, because today's theorem says R of K and K bigger than or equal to N. Last time's theorem was saying that R of K and K bigger than N. So this is just slightly weaker, but today's theorem has the advantage that it can be used for any values of any integer values of N. Of course, being positive, bigger than or equal to 1, and K has to be positive integers, but that's the obvious condition. But once you have that, any N and K positive integers, we can allow to use today's theorem. But last time's theorem, we needed to have this number here to be less than 1. Okay. So now let's prove this theorem. Proof of theorem. Okay, so we are given N and K, and we want to prove that capital R of K and K is bigger than this number. Okay, so how can we prove this? So to prove this theorem, if you remember, so let me tell you about the idea. So we saw that if we have a red-blue coloring of Kn that has the property that has no monochromatic copies of Kk in it, then capital R of K and K has to be bigger than N. So this is something that we also used last time, and today we are going to also use. Now, to prove the theorem, so consider a random red-blue coloring of Kn. Okay, so consider random red-blue coloring of Kn, and let A1 be the event where let's say, for example, V1 to Vk is a red click of size K, let A2 be the event where, let's say, V1, V3, all the way to Vk plus 1 is a red click. Okay, and so how many such AI do I have? So I'm going to consider, random red-blue coloring of Kn. Well, Kn has n vertices, so I'm calling them V1 to Vn, okay? So I can say that this bit, the set of vertices V1 to Vn. Okay, so these are the set of vertices. Now, it's a random red-blue coloring. Now, my first event is the event where V1 to Vk, the first K of them, is a red click. Red click means complete graph. Complete graph with red edges, all red edges. Okay, now A2, I'm going to, for the second event, I'm going to consider another event again with another graph again with k vertices. Now for the first event, I consider the first k of them. Now for second one, I can choose another k vertices such as v1, v3 to vk plus 1. Again, I require this to be a red click. This is my second event. And so on. So, so how many such elements, such events do I have? Because in each event, I'm going to choose k vertices out of n vertices. So in total, I have n choose k choices. So we have n choose k such events. Similarly, let v1 to vk, let v1 be the event with v1 to vk is a blue click, again of course of size k. v2 be the event where v1, v3, vk plus 1 is a blue click. And again, we have n choose k such events. Okay, now define the random variable x as follows. So x, capital X, I'm going to define it as 1a1. So the indicator random variable corresponding to a1 all the way to 1a n choose k. Remember we had n choose k such events. Then 1b1 and again n choose k such events. Then e of x is equal to p of a1 all the way to p of a n choose k plus p of b1 plus p of b n choose k. Remember to prove this, right? That if I consider indicator random variable, expected value of such random variable is probability of the event. Now, what is probability of A1? That, you know, V1 to Vk is a red click. So that means we already calculated this last time, if you remember. It was 1 over 2 to power k choose 2, right? So similarly for other AIs and also other BIs, you can also look at the last time's lecture. We explained about this. So each of these PAIs are basically 1 over 2 to power k choose 2. How many of them do we have? So we have n choose k of AIs and again n choose k of BIs. So 2 times n choose k as 1/2 to power k choose 2. And if we simplify this, this is n choose k times 2 to power 1 minus k choose 2. Okay, so we showed that the mu equals e of x and equals n choose k times 2 to power 1 minus k choose 2. Okay, now by remark above, P of x less than equal to mu is positive. Okay, this is what we proved in the remark right before this theorem. Okay, so what does this mean? P of x less than equal to mu is positive. So that means there exists a red-blue coloring of Kn with at most mu monochromatic copies of Kk. Okay, see, if this is not the case, if for every red-blue coloring of Kn, we have more than mu monochromatic copies of Kk, then P of capital X less than equal to mu would be 0, not bigger than 0. And note that capital X here, what does capital X represent here? Capital X here represents or measures the total number of monochromatic copies of Kk. Because every monochromatic copy of Kk is either a red click or blue click of size K. And capital X measures all of them, addition of all these indicator random variables. Okay, so P of X less than equal to mu is positive, means there exists a red-blue coloring of Kn with at most mu monochromatic copies of Kk. Now choose such coloring of Kn and delete one vertex from each of these monochromatic copies of Kk. Okay, why do we delete one vertex from each of these copies? Okay, let me explain for you. So suppose a number of monochromatic copies of Kk in this coloring of Kn is M, and of course M has to be less than or equal to mu, because we just said that there is a red-blue coloring that has at most mu monochromatic copies of Kk. Okay. Now the claim is that the new complete graph of order n minus m has no monochromatic copies of Kk. This is the whole idea, to show that capital R of K and K is bigger than some number, let's say L. I have to find the red-blue coloring of KL that has no monochromatic copies of Kk. Okay, so now Kn had at most M monochromatic copies of Kk. I deleted one vertex from each of those copies to basically ruin those copies so that they are no longer be able to be a monochromatic copy of KK. Okay, so once I delete one vertex from each of those copies, in total I had n vertices. I deleted m of them. When I said delete a vertex, of course you have to also delete all the edges connected to that vertex as well. So, but how many vertices? I'm focused on the number of vertices here, not edges. So how many vertices am I left with? I'm left with n minus m vertices, and this cannot have any copies of KK anymore. Why? Because if it had a copy of KK, then that would mean the original Kn has to have at least m plus 1 copies of KK, because those m copies that originally existed in Kn, I ruined them by deleting one vertex. They are no longer monochromatic copy of KK. So if this new complete graph of order n minus m still has one copy of KK, monochromatic copy of KK, the original Kn has to have m plus 1 copies of KK, which is not possible. I assume that the original KK has m copies of monochromatic copies of KK. So let me explain this way, copies of KK. Otherwise, the original Kn, like the original red-blue coloring of Kn would have at least m plus 1 copies of monochromatic copies of KK. KK, which is not possible. Okay, so this means that capital R of K and K is bigger than n minus m, which is bigger than or equal to n minus mu. And this is because m is less than or equal to mu, so n minus r is bigger than or equal to n minus mu. And this is n minus n choose k times 2 to the power 1 minus k choose 2 as desired. Okay. So using expected value, basically today we use the expected value and the fact that expected value of an indicator random variable is P of A. And also one result from probability that P of X bigger than or equal to mu and less than or equal to mu, both of them has to be positive. And we use that to prove the existence of the structure that we were looking for. Okay, so yeah, that's all for today. Thank you and see you soon again.